Calc 2, Lecture 10. So the beginning of this lecture should be something that you're very familiar with, and that is volume of a solid. So we are talking here about volume of a solid. And in calculating the volume of a solid, there are technically two methods. The first method is what usually is what is required on the AP exams, if that's what you took, and that is the volume by method of cross sections. And the premise here is that you are taking a cross section like a slice of the bread, and you're looking at what that area of that slice is, that cross section, as a function of the variable of integration that you're going across. And so do a little bit of hopefully a decent job here. We are going to look at this in 3 dimensions, where this is z, x, y. So this goes straight down. This goes over here. This goes here. And the premise, sorry, let me go positive y over here. Oops. There's my y right there. So if I have a function y as a function of x, such that maybe the function looks like this, then my cross-sectional area, and actually let me just bring that all the way down here. What happens is that of course, you know the idea that if I'm revolving it around, we have this function right here, and it's going to bring apart another area over there. It's also gonna, right here. And we are going to have some piece of it. I want to do a decent drawing here. It's been a while since I've drawn these. Right here. So we have this 3-dimensional shape here that is starting from some value A and ending at some value B. And basically, I'm going to just try to pull it out a little bit better here. There. If I just look at one little slice of this, this is what that little slice would look like. So now this is not from A to B, but this is just the idea of one little slice of what this looks like, where this right here is my delta xi, some value for delta x sub I star. So we have right here, this would be x sub I minus 1. This would be x sub I right there. And then this picture right here basically represents delta A sub I, or that cross-sectional piece right there represents delta A sub I. The area of that cross-sectional piece right here. Okay? So if I want to find the volume of this piece, well, delta V sub I would therefore equal to delta A sub I times delta X sub I star. The area of that piece, little piece right in there. Basically, we understand that here that volume. So when we did the height, it was just when we did area, it was the height of that rectangle, f of x sub I star times that. So, I could get rid of the x sub I star, not really important, the star portion of it. But volume is equal to the limit as n approaches infinity of the summation from I equals 1 to n of a of x sub I star times delta x. And the reason why we can just use delta x versus delta x sub I or delta x sub I star is that we're just saying that it doesn't matter what that width is of delta x, as long as if it doesn't matter, then we can keep them all the same. And with this, you get the formula that you should probably be comfortable with, that volume, when we know the cross-sectional area, is equal to the integral from A to B of the area of the cross-section, A sub x, or A of x, dx. Or we can also write this that the volume, if we were integrating from bottom to top, we can also say that the volume, if we are able to find a formula for the same cross-section as a function of y, then A of y dy. So you can find the volume either way. It just depends on how it is that you are calculating, or if you are given a cross-section. That's the key thing. So you need, if it is a one-to-one function, and you can find the area of the cross-sections as a function of x, or its inverse as a function of y, and you can go from A to B or C to D, then these two areas would definitely be equal to each other. As we go on to this lecture, this is why when we do stuff like shell method, and when we do it with dy versus dx, or dx versus dy, you can get the same area. You'll get the same volume. But that does not just mean that if you switch the limits, you're going to get the same answer. So that's the general formula. And, there's some, if I give you that this is the area of the cross-section, and I say this is the cross-section, it doesn't mean that there has to be a pi or something, or doesn't have to be something squared inside that area of the cross-section. What is the function of it? Now, there is a little bit more applications in here that, based on the image, you can find the area of a cross-section, and it will either have a pi because you're revolving, or it might have something like a square or two functions multiplied by each other, because that's how you calculate that area of the cross-section. So when we do something like perpendicular cross-sections, also known as volumes on base, you are doing the cross-sectional method. A lot of the misconception here is that when students hear volumes by cross-sections, they're only thinking of revolution. But when you're doing volumes on base, you are essentially doing cross-sections. So let's say here's our region. Here's our base for our region. So this is the region right here. This is R. And, R is going from A to B, and we have some function y equals f of x. And, we have some other function, or, we have the x-axis right here. This is y equals 0. Then we know from our previous thing that R is just equal to the integral from A to B of f of x minus 0 dx. So we find the region of R. Bless you. Now, the same values that we use for A and B will be the same values you use for A and B for volume. And what we refer to this oftentimes is we refer to this f of x minus 0, or just f of x. We refer to this as the chord. And so that chord right here is that right there. And we're going to use that for the volume notation that I'm going to use very shortly. Now, what are so the most common cross sections, for example, when we're doing here, if I say that we have perpendicular cross sections, that perpendicular symbol right there, and I say to the x-axis are squares, we need to understand when it says this dx perpendicular to the x-axis, then our formula is going to be what? What is our variable of integration going to be? Dx. And the reason is that when I'm building these cross sections will be going from starting from my left going all the way to my right. Starting from A, from the area of that cross section, going all the way to B. There is a visual of this, and I'm going to post it inside Canvas, so it's just a little bit more of a visual if you're having trouble seeing the visuals of this. The idea is that these are sweeping across, and that at some X right in here, we're going to get a cross and one more last cross section. And it's basically this cross section right there is what I'm trying to look at, which is in this case the area of X. Okay, so this cross section that occurs right there at X is what I'm looking at. And so my volume would be equal to the integral from A to B of that cross section, which is a square, which would be f of x minus 0. I'm not just going to put that f of x, that minus 0 there as pointing, squared dx, because a square means that this side here, that all the sides, of course, are equal. And so the length, the base of that square is f of x minus 0 squared. I'm going to show you a little bit differently. Now, if I said perpendicular cross sections to the y-axis are squares, then the volume is going to equal to the integral from C to D of whatever that chord is as a function of y squared dy. And we'll talk about what that chord is, and how those formulas are in the next piece. Taking some questions out there. Any questions? Any visuals, issues? It's whatever the chord is as a function of y. So if I was going from this image right over here, then the chord would be from here to here. This is C of y in this image. Whereas over here in the blue, this is C of x, which turns out to be f of x minus 0. So when you're trying to find the chord as a function of x, it's just going to be y top minus y bottom. Versus when you're trying to find the chord as a function of y, I don't know why I did look like that, as a function of y, it's going to be x, the right function, minus x left, the left function, in terms of y or in terms of x. So I like to oftentimes find these as a function of c, and trying to memorize, instead of trying to, some of you probably, if you've done this, you probably have the formulas mostly memorized of all of the shapes that you need to be able to do. But let's talk about, or also let me just say that this is going to be a dx, and then this is going to be a dy. Let's talk about the various shapes that you need to know. So here we have what the cross section is, and what is the area in terms of C. Now I'm just going to write in terms of C. Remember, C could be y top minus y bottom, or f of x minus g of x, or it could be f of y minus g of y if it's dy. It just depends on where the perpendicular cross sections are, whether they're perpendicular to the x-axis or the y-axis. So pay attention to that little piece. The first one we just talked about is squares. And in squares, the area of the cross section as a function of x will just be what? C squared, yeah. And then you would replace that. So the idea here is, you would do like, if you want to turn it into a function of x, it would be like, f of x minus g of x squared, something like that. I'm not going to write this for all of them, but I just want to show that one. The next one that we have as a cross section that we should know are rectangles. With a height of dot. So when I put the ... because the height might not necessarily be given to you, and so there's really going to be two types of of ones right here. One is that the areas in terms of C will be C times whatever that h function is. Okay, so they might give you a function and say it might be as a function of x or a function of y. They might give it to you, or the area as a function of C is going to equal to k, a constant, times C squared. And this is when it's like k times the base. Where the height is, and this one right in here is where is h is a function. So if they give you the function, you just multiply the two functions, your chord times the function. If they give you something that's, if it's given that the height is 4 times the base, then it'd be 4 times c squared, because it's c times 4c, which gives you 4c squared. Semicircles. Now, the formula for semicircles often confuses a lot of people, of y, it is 1/8. And the reason that it is in here, and I'm going to put this as a kind of semi-little proof here, is we know that the area of a semicircle is 1/2 pi r squared, right? But in this case, r, the radius, is equal to what? C. It's not c. It's half of c. So the radius is actually 1/2 of c, because the semicircle is the diameter, the chord represents the diameter in the semicircle. And so if I plug these two in, I get, once I've expanded it all, I get that area in terms of C is equal to pi over 8 C squared, because that 1/2 is going to get squared, which gives you a 1/4, and then the 1/4 times the 1/8, 1/2 gives you the 1/8, or just simply pi over 8. Most of these problems, the only difference is whatever that coefficient is going to be. More often than not, it's going to be c squared. Doesn't mean always, though. I would say maybe like 8 out of 10, 9 out of 10 problems will be chord squared, and the only thing that will change is that coefficient. Equilateral triangles. Okay, so we have equilateral triangles. I'm not going to go into too much in regards to I guess I can. We have a little bit of time, right? So if I have an equilateral triangle where this whole length here is C, then the idea here is I need to find the height of this. And so this right in here would be C over 2. This is C, and this would be a 30, 60, 90 special right triangle now, which makes the height of it what? Square root of 3 over 2, right? C times the square root of 3 over 2, 30, 60, 90. And so we get, basically, this is why this formula is as it is. The area of, as function of C is square root of 3 over 4 because the 1/2 base times height, right? Area equals 1/2 base times height. So the 1/2 times the square root of 3 over 2 gives you a 4 times c squared. Again, only thing that changes is the coefficient. Isosceles triangles with leg on base. So the base is one of the legs, and since it's an isosceles triangle, that means the height is also equal to the same value, which means that it's the base. So area as a function of c would just be 1/2 c squared. This is different than an isosceles triangles with the hypotenuse on the base. When the hypotenuse is on the base, the problem becomes very similar to the equilateral triangle, but instead of a 30, 60, 90, it's a 45, 45, 90 special right triangle, which is going to give me that square root of 2 over 2 being the base, or 1 over square root of 2. So you get 1 over square root of 2 times 1 over square root of 2 times the 1/2. And so you get the area of C is actually 1/4 c squared. So basically, you should think of it like, I know the equilateral is square root of 3 over 4. If it's the isosceles with on the hypotenuse, it's going to be over 4 as well. But the hypotenuse versus the leg being just a nice, easy one to be able to see. Okay. Questions? Questions on perpendicular cross sections? So find the area of the region like you normally would. Find the region of the area, and usually these, if the question requests you to find the area of the region, then do so. But once you set up the area of the region in respect to the variable, those limits are going to be the same and the functions are going to be the same. So if it says, when finding the area of a region, you have the option to go dx or dy. But when I say perpendicular cross sections are, x-axis versus y-axis, you have to do it as a dx or you have to do it as a dy, if using the cross-sectional method. Which, if they're all cross sections are there, then we have it. This leads us to volumes of revolution. By cross sections. So we're going to talk about it by using the cross-sectional method, which is basically the method that most all of you have probably already seen. Some of you might refer to this as the disc/washer method. But do know what you're doing here, or what we are doing here, is cross sections. Okay, so it's technically cross sections. It just turns out that when we do these types of problems, and we have some type of function, y equals f of x, then when we want to find this volume, and it's in this example, in this visual, when we revolve it around anything, in this case y equals 0, then the cross section, so here's A, here's B. If I look at a cross-sectional point at a point X, then every time I revolve it, this cross-section will always give me a what? It'll always give me a circle. Where the chord, so I can go through all of them, but that's just one of the cross sections that's going to happen at that one piece. But all of the cross sections will always be a circle where the radius will always equal to the chord. And in this scenario, the chord is not the diameter like the previous one, but the chord is actually the radius. Okay. Yes. Okay. And we know that the area is equal to pi r squared, so the area is technically equal to pi c squared. And so with combining both of those together, we would get that the area as a cross section, well, actually is pi c squared. So the volume is equal to the integral from A to B of pi times y top minus y bottom squared dx. Now, in this problem, there's a couple of things that I have to do. Now, this is what we refer to as this is a couple of things are true here that we have to put disclaimers on. One of them is that this is a disk, which means that the that part of the region is, and I'll use the word flush to the x-axis. That's one part. The second thing that we have to understand here is that we're revolving, on this example, we're revolving about the x-axis. And the last thing I want to note about this particular formula is that the region is above the x-axis. So there are three different things. So this is not like our formula for our forever formula. All right, so this kind of has a couple of different understandings here in regards, well, it is flush. So we would get, if all three of these were true, of course, we get that the volume, in this case, the y bottom is 0. Or I said bottom, y bottom, but it's really just the x-axis. The volume is equal to the integral from A to B in this example of pi f of x squared dx in this piece. And of course, yes, there's a couple of things. What happens when we don't have a function that is flush? So in this case, y bottom was 0, right? Y bottom was 0. It wasn't a function, it was 0. So that makes it flush to the x-axis. The second thing, of course, is that the whole region was above. And so instead of using top and bottom, we're going to flip that and say outer versus inner function. Because if the region is below, to correctly set it up, which I'm going to take points, is that it might be bottom minus top, because you want to get a positive radius value every single time. And if you do top minus bottom, where the entire region is below, then that would give you a negative region. And it will still lead to the same answer because of the formula having this squared, but it doesn't necessarily mean. And I know most of you will write this as volume equals, you'll write the pi on the outside, A to B, f of x squared dx. This is also perfectly fine. But I want you to note that pi that you're seeing in there, in this formula, comes from the cross section being a circle, where the radius is that chord. Okay. So what about all the other scenarios? And that's what we're going to go on before we go on to break. We'll cover that real quickly. So what happens when we don't have a constant for the other function, or it's not 0, it's not the x-axis, all of these different scenarios. So let's look at this example right here. So we have y equals f of x. We have y equals g of x, and we are going from the region from A to B as such, and we want to look at, so what I like to do here when asking yourself, if you can sketch the region, and in this case we're still going to revolve around the x-axis. Okay, so you find your axis of revolution, which in this case is just still y equals 0. You find a point in the middle, that's your x, and you go up. The first function you hit, this length is the y inner. And the second function that you hit, if you go on, this whole distance here is our outer. Some of you might use big R versus little r. I'm not a fan of big R versus little r because big R is usually represented the region, and then you're like, big R is this, but then big R is what big R, and it gets a little bit confusing there. So I like to use R outer versus R inner. And so in this formula right here, a function right here, R outer is f of x minus 0, the axis of revolution, and R inner would be g of x minus 0, the axis of revolution. And of course, we'll talk about what happens when we're just any line. So when revolving about the x-axis, volume will equal, now basically what we need to understand, and this is where the correct word, this isn't a annulus or a donut, a washer, where this piece right here is my R inner, and this part over here is my R outer. And if you know how to find the volume, or the area of an annulus, the area is equal to pi R outer squared minus pi R inner squared. Now, depending on how you like to do these, so sometimes some teachers will just teach it as just take two integrals. So who here has been taught this by doing an integral minus integral? Okay, and everybody else, I'm assuming that you've been taught this by just one single integral? Both of them are correct, just how you want to be able to do it, because this is also the same thing as just pi times R outer squared minus R inner squared. And so it just sometimes makes it up if you do it as one long integral. That's why it's easier. But what you're really doing is pi times the integral from a to b of R outer squared dx minus pi integral a to b of R inner squared dx. But like I said, we can just make this as 1 pi times the integral from a to b of R inner squared minus R outer squared dx. And this R outer and R inner will work no matter what your axis of revolution is. I got outer and inner backwards? Yes, I did. Out versus in. There we go. And so in this example over here, from this example here, my volume would equal pi times the integral a to b of f of x squared minus g of x squared dx. And again, if R inner is just 0, meaning it's flush, then you have a disk which doesn't have the two. There's just one radius. It's just one solid circle. I personally like, if you just follow, I always like to do the R outer, R inner method for all of them, DYs. It just makes a lot of things a lot more simpler in my mind for doing them. Just talking about what happens when you revolve around something else. So if we have, once again, this region where this is y equals f of x, and this is y equals g of x, and we were to revolve, instead of the y-axis, some y equals k, all that's going to do, once again, drop it right here. This is R inner, and then this is R outer. And so R outer would just be f of x minus k, or if the region was above, right? If the region was above, then if I go from here to here, then R inner would be k minus f of x. So K minus would be the length from here to here if the region was above, or if the whole region was below, depending on where the axis of revolution is. And our inner would be G of X minus K. It would flip on the opposite if the region was revolving the other one. And again, if I was doing this, volume would equal pi integral A to B of, I like to use parentheses here. It would be f of x minus k squared minus, bracket, g of x minus k squared dx. Again, it just comes down to being, which one is going to be the top and which one's going to be the bottom. If I was revolving parallel to the y-axis, okay, and once again I'm using cross sections, then my volume is going to equal to the integral from C to D of pi times r outer squared minus r inner squared dy. So the r outer and the r inner still stay there in terms of your base formula, but now it's a dy problem if I'm revolving parallel to the y-axis. And if you're wondering, what do you mean by that? If this was my part right here, and I had the function like here, and I had the function like here, and this was this is y equals f of y, and this is y equals g of y, and this is d, and this is c. And I was revolving it around k. And let's say, actually, let me flip it over here. Let me put k over here, okay? So this is x equals k, so x equals 5. Remember, the y-axis is x equals 0, all right? So you can use minus zeros. And so, once again, what I always like to do is I say, okay, boom, that's our inner, the first one I hit, boom. The second one I hit from my axis is r outer. So my r outer in this case would be k, which is bigger, minus g of y, and r inner would be k minus f of y based on the image that I draw. If the axis of revolution was to the left of the region, then it would be the function minus k. So this is, again, this is very similar as if I was just to, like here. So if that axis of revolution was above the region, then it'd be k minus versus the one that we have right here. So my point is here, if you draw it from your axis of revolution, then you're fine. And then all you have to do is slap those two values. You just have to replace these r inners and r outers with what they are, and then you do the calculus. You integrate. Mm-hmm.
So you have y equals g of x and then y equals g of y.
No, they're both y's.
They're both y's.
Yeah. They're both y's. Now, I could give you one of the functions as a function of x, but in that case, you have to solve for x equals. So typically that happens with a one-to-one type of function. So in a one, as we get into the next part of our lecture after break, you do have options to do the problem here. And so how the problem is presented to you. Do you have a function of x versus a function of y? Because what happens if I was revolving in parallel to the y-axis, but I don't have a one-to-one function, and I give you y as a function of x? Well, cross sections is impossible to do, or you're going to have to do all kinds of weird little things and additives and break it down in different regions. And no, there must be another method, and there is. We'll go out of a break. It is 11:20. Okay. All right, so let's continue. And what we're going to talk about in this part now is we're now going to talk about volumes of revolution. By the shell method. And now, in AP Calculus, both AB and BC, the shell method is not a required problem to be able to understand and how to do. Some teachers, some of you may have been exposed to the shell method in AP just because your professor might feel that there's some problems that you could do on the AP exam that might lend itself to the shell method to be easier. It's very rarely. On the AP exam, if there was ever a problem that the shell method could be used, it's always a one-to-one function like y equals e to the x or some linear function where you can solve back for the other variable. And that's why you don't have to do the shell method. You could always use the cross-sectional method and just do a dy. But what happens if we want to do dx for those problems? So the premise here, and this is a big visual, is let's say we have this function. And for the purposes of this image, let's say that the function is just one function, y equals f of x. Okay, and so the region R, this right here, from A to B is our region. But instead of revolving this region about the x-axis, parallel to the x-axis, y equals -2, y equals 0. Doing something like y equals 3 would be just terrible because the region would like revolve on top of itself. We're not going to be trying to do those type of problems. Don't worry about that. But let's say I'm revolving about the y-axis around x equals 0. If I was going to do that, the method I would need to do, because I'm revolving parallel to the y-axis, you would think, oh, if I'm using cross-section, I have a dy. But y equals f of x. But what happens if we want to leave it as a function of x, or we want to leave as a dx problem, or we cannot solve for x equals a function of y. So in other words, dy is out of the picture, okay? So sometimes you could do it both ways. If the function is a one-to-one function, you could do it both ways, all right? The problem with doing cross-sectional method here is that you would, in fact, need to do two different regions. You'd have to, like, break it up and be like, boo, 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 boo. You know, that little region right there, and you have a different top and you'd have a different right and left functions, so you'd have to do two regions stacked together in two volumes, right? But instead, what we're going to do is we're still going to revolve this region about here, and when we revolve this region around, we'll take a little tiny sliver right here. Okay, we're going to take a tiny sliver, and we're going to revolve this around. So this is still dx right here, and we're going to revolve that about the x-axis. And this is what we would get when we revolve it. So in the previous one, we were doing like a dx, and it was a really thin, it was a dy, so it was a really thin top, and then we were swinging it around, which technically doesn't create a full circle. It actually creates a cylinder, where we have the volume of that cylinder for that cross section would be the circle cross section times dy. That's what we did on the previous problems. So when we were revolving these, technically there's a little bit of depth to this, and so the volume would have been, so you technically have a little dx right in here. That's what I was trying to show. So it's the area, the volume is the area, the circle area times dx. That would be the volume. Whereas in here, now we're revolving it this way, all the way around, and so we need to figure out what the volume of this piece is. And so what we need to recognize is that we do not have a disc or a washer, type of volume, but we have what's called a shell. Okay? So in this picture, some other things that I need to represent. Actually, I can just I'm gonna just draw the shell on a separate page. Okay, so and so we have again. If I reflect it across the other side. Like this, right? I see it's more in the center right there. And when I'm looking at this shape, it's like this. Just making it a little bit more prettier on this. And there. You see this? Do you see the shell now? Okay. It's like it's like a cylinder with a cylinder removed from it. So just like the annulus, where there was a circle with a circle removed from it, the volume is basically a cylinder with a cylinder subtracted from it. Now, in this image, we're going to define the distance from the center to that first piece as R1, and the distance from the center to the other piece, we're going to call that R2. The distance from here to here, that is, of course, delta X, which we'll define as the letter T, like thickness, which is R2 minus R1. The thickness of the shell is R2 minus R1, which is coming technically from that dx piece. And the height of the shell is f of x sub I star. Okay. Now, it should be understood that where this height comes from, we need to figure out what x sub I star is. And so to do that, we're going to find the center of this right in here. So right in the center, and we're going to call that the average of R1 and R2, which is R bar. So R bar is the average, the center of R1 and R2, which is therefore R1, and I'm going to do it the other way, R2 plus R1 divided by 2. That's the center of R1 and R2, these two radiuses, which is x sub I star. That's where x sub I star is coming from. It's in the center. It's somewhere between that partition because it's remember the ith interval? So we're looking at here, basically, when I chop this up, I found one region, one slice, x sub I minus 1, or x sub I minus 1, x sub I, and I have to pick some value between that region for where the height is going to be found. Okay? So, just as a reminder, the volume, remember we said it's like a cylinder minus a cylinder. I know that was your final design, right? Pi r squared times h. So given this formula, we want to find the volume of the shell would therefore be equal to the volume of the outer shell, or outer cylinder minus the inner cylinder, which is pi r2 squared times h minus pi r1 squared times h. Right? Which gives us pi h times r2 squared minus r1 squared. So that would be the volume of one v sub I. The volume of one individual shell. And we want to find the volume of all the shells, and we add up the volume of all the shells, and then we would get the actual one. But we need to turn it in terms of I, right? So this is like a delta, this is not v sub I. The correct notation would be delta v. There we go. Now, if you recall, we can write this now as, well, this is a difference of squares, so we can write this as R2 minus R1 times R2 plus R1. Yes? And I can multiply this whole thing by 1. I can multiply it by 2. And I can divide it by 2. Yes? Did I change it? No. So now we have that this volume is equal to 2 pi h R2 minus R1 times what? R bar. What is R2 minus R1? T, yeah, so it's the thickness, which is delta x. And R bar, we said, is? Well, that's how we got it, R bar. Is xi star. And we also can note, when we've noted here, that the height is equal to f of x sub I star, right? So we get that delta v is equal to 2 pi x sub I star times f of x sub I star times delta x. And what that does for me now, it says, well, that's the volume of one of them. We know that the actual volume would be the limit as n approaches infinity of the summation from the first shell to the last shell of 2 pi x sub I star times f of x sub I star delta x, which gives me that the volume is equal to what? The integral from a to b of 2 pi, what? 2 pi, what does x sub I star turn into when we turn it into an integral? X times f of x dx. Now, most people remember this formula as volume equals, they'll put the 2 pi out in front, integral a to b, and they might write it as x times y dx, something like that. What's important to note here, and the biggest thing that I see, so this y, this y right here, something additional to note here, that if I was revolving around, I'll wait right here, let you copy down, and I'll draw one more image to help you. This x right here is representing the the radius, right, of each shell. That's the R bar, or that represents the radius right there. And the Y represents the height of that shell, or of the cylinder, it represents, right? So however you want to think about it. So when you're thinking about this, the shell, volume equals pi r squared h, r squared h, the r is coming from the x, or the x is coming from that r rewritten, and the h is coming from the height portion of it. Now, why do I say that? Because if I were to give you y equals f of x and y equals g of x, and we were revolving around that point over here, x equals h, where it's it's bigger, right? Like this, then the height represents, so when I drop down this point in here, this is x. I'm going to go from A to B, and so this height I can see here is f of x minus g of x, right? But what is the radius?
X minus
Close. So r is h minus x. And the height, I kind of did the same. Let me use a capital H here. I'll use capital H. Capital H is there. The big H would be f of x minus g of x. So when I'm doing volume here, I would do that 2 pi integral a to b, and it would be x minus h times f of x minus g of x dx, like that. So the h, the y, represents the height of that, as we normally, which is like the chord. It is the chord. And the radius is the distance from that axis of revolution, where how wide each shell is actually going to be. Okay? What happens if I'm parallel to the x-axis, but I want to do a dy problem, or in other words, I have only x as a function of y, and it is not 1-to-1. Remember, 1-to-1 represents the idea that you can solve for the inverse function, or x equals versus y equals, and you would still get the same function. That's what I mean when I say that 1-to-1. E to the x, y equals e to the x, y equals ln of x, y equals 5x plus 2, all those type of functions, where if you solved it for the other function, you would still have a function over its domain. Y equals x squared, doesn't work, because you have square root of y, right? X equals square root of y plus or minus, doesn't work. Then you get some funky equations and functions, which doesn't work. Well, the same thing, I'm not going to go through the proof here, but in using shells, the volume is going to equal to the, once again, 2 pi integral c to d of the height of the radius, right, times the height dy. But the problem here is that the radius is now in our visual. The radius, I don't want to color too much. This part right here. And so, well, you still get the same exact formula, but the formula is now 2 pi integral c to d of yx dy, where y represents, and it's still like most people just remember, it's still xy, it's still xy. This y represents the radius, and this x represents the height. And so volume is equal to 2 pi integral c to d of, y minus k times x right minus x left dy. But here's what I want you to note. Both of the formulas shells with dy dx, shells with dy, volume equals 2 pi integral a to b x y dx versus volume equals 2 pi integral c to d of x times y dy. Most of people say, okay, they look to be both the same formula. And this is going to be important when we do surface areas and arc lengths and stuff like that. But because this is a function of x, that means I need to change this to a function of x. The x stays in the formula, okay? The x will stay. You do not change the x because it is in terms of dx. Versus over here, since this is dy, the y changed, the y stays, and I need to convert this to the function of y that is being used, the top minus bottom. So this can also, for me, this helps me understand that the one, when I'm doing shells, the function that I'm changing, reality here is a good sketch will figure out which one's top and bottom and which one's your radius. All right, and then you can plug it in there. A good sketch will get you there. But with the way I always like to think of it is, well, if I do it this way, then I know that the function that I have to change over is coming from the height function. And then the other one is therefore my radius. So I have to change x because it's a dy problem. I can't have x's and y in my integrals. And there we go. Let me see here. I think I can. We got 7 minutes. I can do arc length. So let's talk about arc length. We can do it. I'm not going to go into. I'm going to cut out a lot of the proof part that I had on a different one, and we're going to go into a different one. Basically, the idea is, and here I have y as a function of x, and I want to find the length of this. I want to find the length from here to here, with all of its curvatures and everything. So I want to find this total type of length, and in calculus we define length as s. Okay, so s is our length. Now, very similar to what I did in all the other ones. Well, since this curve is curving, why don't I just chop it up, right? Why don't I just chop it up, and so forth. And I would try to, if I chop it up into nice little pieces, then at some point those pieces are so thin that they're all straight lines, even if they're curving. And so I'm going to chop this piece right in here, for example, where this is x sub I minus 1. What is that? I heard something. And this is x sub I right there. What is that? You need more time here?
No.
He's just very happy today, yeah.
I'm so happy to be here.
Yeah.
So that little piece that I am now trying to find right here, if all of those pieces, if the whole thing is s, then this piece is ds. Okay, if I zoom in long enough, that little part from right here is going to be a line like this, and therefore there is a dx portion of it and a dy portion of it. And so this is called utilizing what we're using a symbolic device here that I like to use. And basically ds is equal to the square root of dx squared plus dy squared. And what is that? What was your question?
But where does the one then come from?
Ah, very good. I haven't gotten there yet. So s, the total length, would be equal to the integral from star to star star of ds. And there's your arc length formulas. Now we still got 4 minutes. I can still go. Star and star star are the lower and upper variables of integration. Based on function variable. So it's based on the function's variable. What I mean here is that you can find the arc length with respect to x or respect to y. What is it a function of? So what do you have a function? Is this function represented x as a function of y, or y as a function of x? If it's a one-to-one function, you can do it with respect to x or respect to y, and you'll get the same answer. So let's take, for example, let's say we have y as a function of x.
Wait, Sammy, can you rewind a little bit? Like, what do you mean that again?
Watch, I'm going to show you.
Yeah, you'll see it exactly.
So if y is a function of x, then what do we want our integral with respect to? Dx. And so we know that our integral, that s is equal to integral from star to star star of ds. But since we want it from as a function of x, then this is going to become the integral from a to b, because it's technically from x equals a to x equals b of ds. Yes? But what is ds? I need to turn ds into dx. And so this is where the symbolic device comes from. So we know that ds is equal to the square root of dx squared plus dy squared. And so what I'm going to do is I'm going to multiply this whole thing by dx over dx. And this bottom dx is going to pull through the square root. So ds is equal to the square root, a big long square root, dx on the top, of dx over dx squared plus dy over dy squared. I'm pulling the dx from the denominator through the square root, which becomes dx squared for the denominator, and therefore it becomes this. Does everybody follow that piece right there? Enough.
Y over dx squared.
Dx. Yeah, that's what, yes. So dx, yeah, dx on both of them. So now this becomes the square root of what? 1 squared, plus dy dx squared dx. And now s is therefore equal to the integral from a to b of the square root of 1 plus f prime of x, which is dy dx squared dx. What happens if x was a function of y? Right?
Wait, Sammy.
Yeah.
The people are asking where the stars went.
I know, that's what the answer is.
Yeah.
The answer is coming from here. So if it's a function of y, I want dy, right? So the integral, so s would be equal to star, star, star in its most basic formula of ds. But I want it as the integral from c to d because it's going to be something dy. I need this whole thing right here was ds, but I need to turn it into dy. So the stars become the new now c to d because my function is dy. So once again, ds is the square root of dx squared plus dy squared. I got like 30 seconds. And I'm multiplying by dy over dy. Same thing happens with that one. And what happens is I get the square root of dx over dy squared plus dy over dy squared dy. And so ds, when I turn it into dy, becomes this. And my star and star star now become the limits with respect to y versus the limits with respect to x. And so s is equal to the integral from c to d of the square root of 1 plus f prime of y squared dy.
So the stars and the stars are just like placeholders in that sense.
They're just placeholders for whatever variable I'm going to integrate it with. And that's where I'm going to end today with at the beginning of next lecture, because we can do this in polar. So star and star star represents theta 1 and theta 2. We can do this in parametric, where star and star star could be x1 and x2 or y1 and y2 of t. Or dt, sorry, t1 to t2. As long as you know the symbolic device, though, as long as you know this, you can rewrite the formula to give you your dx or your dy. So I'm going to remove the surface, and then we can go to surface area, which is arc length as well, and it becomes even more funner. So we'll do all that in our next lecture. I'm going to remove the last two problems from your P set. The surface area and the improper integrals, those will be moved over. So in the homework, in the P set problem, the first arc length problem I've given you is an implicit function. You need to decide, and I gave you both the x and y coordinates of both of them. So you need to turn that as x equals or turn that into y equals. Whichever one is you're able to do tells you if you're doing dx or dy. And then you just use the limits for x if it's dx, or use the limits for y if it was dy. Good? Okay.
The stars are just funny.
Yeah, and
I get that they're just placeholders, but since it's like a funky symbol, it was just funny.
yeah, so because it's for ds, so it's the limits for the ds, but are you going to do it with respect to x, respect to y, respect to t?
You haven't defined it yet. You haven't chosen it. I understand. It was just funny.
No?